Welcome back to the last topic that we are going to be looking at. And this is another topic on more derivatives. Today we're going to be looking at something called implicit differentiation. It's a big word. Differentiation just means it's taking a derivative. I can't figure out what part of speech that is. I think it's a tense of verb. But anyway, and implicit, we can take derivatives of implicit functions. So far, we've only used explicit functions. Explicit functions are ones that can be written as y equals something with x, or f of x equals something with x. Implicit functions are functions like the graph of the heart I have up on the front of the board, where we have x's and y's all scattered out, and you can't get it to equal y equals something. Although it does work for that stuff too. And honestly, I do most of my differentiation implicitly. It's an easy next step to turn into the regular. Anyway, looking back at our derivative notation that we saw last chapter, we have a couple ways of writing the derivatives. There's the f prime of x, or y prime, which is what we've been using. But there's another way that I said is it can be easier in doing certain stuff. This would be one of those certain things, and that would be dy over dx. Remember, this comes from the whole idea that the derivative is a slope. It's a change in y over the change in x. Change is a capital delta. Well, it's a very little change, so we use the lowercase delta, which just kind of morphed into a d. So dy over dx, and dy is a derivative of y, dx is a derivative of x. And you might be thinking, well, the derivative of x is 1. It's 1 times dx. So if we look at something like just y equals x squared, how could we do this implicitly? Well, we can find the derivative. The derivative, dy over dx equals 2x, right? Just power rule. And that's what we've been doing. And notice I have the y prime. Well, that could be dy over dx. Well, instead of that, let's do it implicitly. Implicitly, we look at each piece. So we have y. What's the derivative of y? That's just dy. And what's the derivative of x squared? That's 2 times x times the derivative of x, which is dx. And then we just want to divide to make it dy over dx, because that's going to be the slope. And so we divide. We get dy over dx equals 2x. That's the exact same thing we got. It's just this one extra step in the middle. I know people asked in chain rule, like, well, how do I know when to stop chain rule? So when you get to the derivative of x, when you get to dx, that's when I stop chain rule. That's why I say, like, happens in my head all the time, but that's largely due to just experience. So let's look at a couple more. So this one was an explicit function. We could have just found the derivative. This one's an implicit function. We have x times y equals 3. To find the derivative here, we are going to use the product rule again. So we're going to have our u's and our v's. And in this case, the u's and v's are going to be very boring, because the u is just x, the v is just y. Du, the derivative of x, is dx, and dv, the derivative of y, is dy. And so we can multiply y dx plus x dy equals, the derivative of 3 is just 0. Now we need to get all the dx's over to the other side of the equation, all the dy's onto the side of the equation. So here's the only dx. We're going to subtract this over. So we get x dy equals negative y dx. Then we're going to divide. We want dy over dx, so the dx comes this way. And we're going to divide by x to get dy over dx equals negative y over x. And then we could stop here because it wasn't y equaled. If it's y equals, we want it to not have y in it. Since it wasn't y equals, we could stop, but we can also go just a little bit further if we want. because we have the y, it's nice to not have y if we can. Up here, we could actually solve for y. Divide by x, so y equals 3 over x, and we can just plug that in for y. Then we can simplify this. We have 3 over x divided by x is going to be 3 over x squared. So you have negative 3 over x squared, which if we went with the y equals 3 over x, y equals 3 times x to the negative 1. If we find the derivative, that would be negative 1 times 3 times x to the negative 2, which is what we ended up with. So this one could have been done explicitly if we solved for it, or we could do it implicitly. Another one, this one would be a lot tougher to do explicitly, not impossible for this particular case, but tougher. But we can do it implicitly. So we have each term we can take separately. We have y squared. What's the derivative of something squared? 2 times the something times the derivative of the something. So 2y dy. And then we'll come back to the 2xy because that's going to be a product rule. But we have x squared. That's going to be 2x dx. And then equals 0 because the derivative of 53 is 0. And now we need product rule here. This product rule is going to look almost identical to this one because it's xy. It's just it'll have 2x for the u. So we have 2x and y. The derivative of 2x is going to be 2 times dx, and the derivative of y is just dy. Notice that all the derivatives are going to have a dx or a dy in them. That's important. So everything here, once we have it, will have a dx or a dy. So we can cross multiply here, 2y dx plus 2x dy, and just kind of plug it in the middle. So we have our 2y dy plus 2y dx plus 2x dy from the product rule plus the 2x dx equals 0. All of the dx's need to move to one side of the equation. All the dy's are already on this side, so they don't have to move. But we can subtract our dx's over to get our dy's equal our dx's. That's negative 2y dx minus 2x dx because they were subtracted. Everything over here has a dy, which can be factored out. Everything over here has a dx, which can be factored out. And then we can divide. The dx will come over here, and then this whole chunk just goes in the denominator down here. So we have dy over dx equals negative 2y minus 2x over 2y plus 2x. Technically, we could stop here. But something kind of cool happens when we simplify this one. And you might be thinking, yeah, I bet something cool happens when we simplify this. Give me a minute. So we can see that, hey, we can factor stuff out here. We can factor out a negative 2, and we can factor out a positive 2. So let's do that. Then we can cancel. So the negative 2 and 2 cancels to give negative 1, and the y plus x cancels to get the derivative equals negative 1. So all this stuff simplifies just to negative 1. Alright, that was kind of cool. But what kind of function gives us a derivative that's a constant? What has the same slope everywhere? A line. A line has a constant slope. Only lines have constant slopes, which means this equation up here is the equation for a line. It's actually the equation for two lines. This is going to be y equals negative x plus root 53, or I equals negative x minus root 53. So this is the equation for two parallel lines. I'll just let that sink in for a minute because that's crazy. But we saw that because the slope is a constant number, and lines have constant slopes. More practice. We can use it for inverse trig. We're not there yet. I just forgot to fade that in, apparently. Natural logs. Yesterday I said that we can find the natural log, but we're not going to do that yesterday. We're going to look at it today. If we have y equals natural log of x, well, what is the derivative of natural log? Yes, we know it's 1 over x because I told you so. But that's the only reason why. So let's work with this and see if we can do this. If we go e to the power, that'll get rid of the natural log, And so this could be written as e to the y equals x. Now we can do the derivative implicitly. The derivative of e to the something is going to be e to the something times the derivative of something, so e to the y times dy, and the derivative of x is just dx. Well, dy over dx we can divide, leaving that as 1. Divide by e to the y. We get dy over dx equals 1 over e to the y. Now we don't want a y in there. So what does e to the y equal? E to the y equals x. So the x can just plug right down in there, and the derivative is 1 over x. That's why the derivative of natural log is 1 over x. We can also do this for inverse trig functions, which I have to say, when I was learning inverse trig functions and the derivatives, the professors were just like, yeah, you just have to memorize these. You can't figure these out. Memorize them. It's a bunch of something or another. We can find these inverse trig functions using implicit differentiation, because we have y equals inverse sine of x, which means we can take the sine of both sides. It's the same thing as saying the sine of y equals x. These two statements are equivalent. Now we can take the derivative. Well, the derivative of sine of something is cosine of something times the derivative of something. So cosine y dy equals dx. We're going to divide, just like we did over here. We'll have 1 over cosine y. But we don't want y in the equation because it's y equals to start out with. So we don't want y. So how could we figure out what cosine of y is? Well, we're going to go back up to this step. We know that sine of y equals x. Remember, trig is all about triangles, so let's get a triangle. Sine of y, that means that y is an angle, and equals x, that's opposite over hypotenuse. Our opposite is x, and the hypotenuse is 1, because this is x over 1. And we need cosine, which is going to be this side over the hypotenuse. Well, that side we don't know, but we can find out, because for a right triangle we can use Pythagorean Theorem. X squared plus question mark squared equals 1 squared, which we can subtract the x squared. So the question mark squared equals 1 squared, which is 1 minus x squared. Then we can take the square root of both sides. So the question mark equals plus or minus the square root of 1 minus x squared, but being that it's the side of the triangle, we don't really worry about the plus or minus, it's just positive. And so that side is 1 minus x squared. So cosine of y is the square root of 1 minus x squared over 1, which is just the square root of x squared, which we can plug in there. And that's the derivative of inverse sine, which is way easier than memorizing because they all work about the same. And you'll be finding some of these, and they all do work the same. You're going to find them, you're going to draw a picture of a triangle, label it, find the missing side, plug back in what you need. Last one, we're going to find the derivative of y equals x to the x. So it's, hey, it's a power rule. It's just x to the x minus 1 times x. No, that doesn't work because that's if you have x to a number. It's exponential. Exponential is a number to the x. X to the x is something different. But we have ways of making this exponent disappear, or at least come out of the exponent, that we take the log of both sides. And I'd recommend natural log because you end up with 1 over something instead of 1 over something with the natural log in it. So let's do a natural log of both sides. And if you take the natural log, you have natural log y equals natural log x to the x. That exponent can come out front. That's why we do logs. Now we can do the differentiation implicitly, where this is going to be a product rule, but the derivative of natural log of y is going to be 1 over y times the derivative of y. And now for x ln x, we're going to have a product rule, where u is x, v is natural log x, du is the derivative of x, dx, natural log dv, derivative of natural log x. It's going to be 1 over x times the derivative of x. We do our multiplication. We have dx times natural log x, so ln x dx plus x times 1 over x is just 1, so it's just plus dx. All the dy's are over here, all the dx's are over here. We can factor out the dx to make it natural log of x plus 1. Don't forget your placeholder there, times dx. Divide by dx, and divide by 1 over y, or multiply by y. So we have dy over dx equals natural log x plus 1 times y, but we don't want y in the equation, so what does y equal? Y equals x to the x. And so, which should make sense, if you have something to a power, you end up with that thing in your derivative, same thing here, then times something else. So, with the implicit differentiation, which you can't really do this one any other way, the derivative dy over dx equals natural log x plus 1 times x to the x. So, I will see you in class for some more practice problems with this, and have a great day.